Oh, okay. So I hope I'm not too loud. So today I want to just introduce some of our recent work focused on grain boundary. I want to acknowledge that the work is mostly done by my PhD student, Xiao, whose affiliation is going to change soon to EPFL. He just graduated and will start a postdoc with Bill. Of course, we all know the importance of hydrogen development, so I won't describe anything here. We know it's a historical problem. And I start with hydrogen ingress into the material, and then segregation at microstructure. And then in particular, the topic is focused on grain boundary, as the title suggests. And we're going to look at the kinetics, basically hydrogen diffusion, not the energetics. But I will make a mention of the tools we recently developed, and I can also characterize the energetics of it. Okay, so as many literature studies suggest, grain boundaries are important entities for affecting the hydrogen environment. And in particular for the diffusivity perspective, there have been studies supporting the trapping slow diffusion, or some studies suggesting that grain boundary facilitate diffusion, or some studies showing that you actually expect a normal diffusion. So there's nothing changed with or without grain boundary. And this is, of course, you see also some studies showing that if you use a different manufacture process, and then you get different microstructure, then you get different diffusivities. So overall, there have been two notions, kind of contradiction notions. One is saying grain boundary facilitating diffusion, so you get fast diffusion. Well, there have been many measurements, and I will make, if I have time, I'll make a mention of that. There's actually really depends on how you measure it, and then you can have different diffusivities, or despite of trapping or whatever. In the contrast, you have other studies saying, okay, and also some data showing that you can have slow diffusion, particularly at low concentration. Okay, so this is one study. I forgot the reference. Sorry about that. So overall, still, it's unknown whether hydrogen and diffusion will be faster or slower with the presence of grain boundary. There have been many theoretical studies looking at local barriers, but the problem of those things, I shouldn't say problem, is that it's quite common because most of the study are DFT calculations. So it's kind of confined by the calculation itself. And then for convenience, the study is mostly localized at the particular region at the grain boundary. And you can see there's a high barrier path and low barrier path. But still, so it depends on how you interpret the results. You can have, well, different conclusion from the simulation. And it doesn't cover the whole grain boundary. So that's kind of the motivation. So I basically quickly go through those slides, and there's a motivation for our study. So we try to really see, okay, so what's the exact role of grain boundaries? And for that, of course, first we need to have effective tools to analyze the grain boundary structure. So the tool we're using is that, so on base of the polyhedron rather than the common CSL method. So what we have, so skip those, is that we use those 3D polyhedron method to describe grain boundaries. So just keep the story short. So what happens is that for any grain boundary or bulk lattice, you can use a finite set of polyhedrons to describe the grain boundary structure. And what's interesting is that for those polyhedrons at relatively low concentrations, then you can only fit in one hydrogen. So effectively, you can use this method to quickly, although sometimes you still need DFT calculation to identify the site of hydrogen interstitial. And then with those hydrogen interstitial determined, then you can quickly predict the hydrogen energetics. And so those polyhedrons also serve as a method that you can actually look at hydrogen migration, because then the hydrogen migration basically happens between individual adjacent polyhedrons. Okay, so this method basically provides you a very quick way to analyze grain boundary structure, and then then combined with DFT calculation, you can quickly get the energetics of hydrogen absorption along grain boundary or in the bauxite, as well as the migration barriers along grain boundaries. So this was published before, like in a separate study. So, but I just want to give a background. This is basically the method we're using. So it's kind of like a space tessellation combined with DFT calculations. Okay, so with that, we can then analyze different grain boundaries. You see that here, like, so basically I tessellate different grain boundaries using the polyhedrons. So you see that it's nicely, you see a series of polyhedrons, and then like hydrogen diffusion would occur as individual hops between the adjacent polyhedrons, okay? Then we can analyze the diffusion barriers for hydrogens along the grain boundary. Of course, it's not just limited to grain boundary. We can then create those maps as illustrated here. So this is just basically the contour maps for hydrogen diffusion throughout the lattice. And one thing I want to mention is that those pictures are all like includes a complete periods of grain boundary. So it's not localized. So if you look at grain boundaries, so it's actually like the full period. So then like, so this is a contour map. So you, so since this periodic, so basically this, if you see the different grain boundaries, if you look at the numbers, then like for the first two, you see the barriers, it's more or less throughout the grain boundary, similar to the bulk barrier. Well, for, I forgot to mention that those blue regions correspond to the low barrier, while the red correspond to the high barrier. Well, for the first two cases, it's very high symmetry grain boundaries. And you see that compared to the bulk and grain boundary, well, there's some slight difference, but overall, the barrier mapping is quite close. So in these two cases, you would expect similar diffusion or diffusivities through the grain boundary. While here, in the second row, you see that you actually have the connected path along the grain boundary all being blue, meaning that you have a connected. So it's really like the key word here is that you have a connected path through the grain boundary that give you continuously low barrier along grain boundary. Well, for the third row, this is a different scenario again. So you see that, again, if you look at localized barriers, you can have a low barrier region, but high barrier regions. But the problem is that there's no connectivity. So you could, if you like look at the hydrogen moving around here, then you would be very fast. But the problem is that hydrogen cannot travel through grain boundaries. Okay, so just from those contour maps, then like we kind of get an idea that if for this different set of grain boundaries, the first set you could have bulk-like diffusivity, while the second set you could have fast diffusion, while the third one you can have trapping, and then like hydrogen, if it's getting into it, and it cannot escape. And by the way, I want to mention that although it didn't show here, but those like high barrier region correspond to like a low energy states for hydrogen. So hydrogen actually prefers to go there. And once it goes there, it cannot escape, or it's difficult. So basically from those mapping, you can see the barriers. And what's more important is that you see the path and the connectivities. So the connectivity is actually the most important part. Of course, this is just local barriers. And if we want to calculate actually effective diffusivity, then we need to do kinetic Monte Carlo simulations, which is shown here. So I didn't describe the simulation details, but that's basically like standard. So if you take all those DFT calculated barrier and as inputs for kinetic Monte Carlo, then you calculate the effective diffusivity for hydrogen from a long grain boundary direction. So the diffusivity we're measuring here is really like for hydrogen diffusion along grain boundary direction. Okay, so the apparently like for this case, hydrogen diffusion can be anisotropic. And it turns out that those kinetic Monte Carlo simulation results can also be well represented by analytical formula. So basically, like so. You can actually, like, if you know the barrier, and the barrier is not individuals, it's actually like effective barrier, and you know the energetics. So this formula takes into not just barrier, but also energetics of hydrogen at Green boundary. Then you can actually predict the kinetic Monte Carlo simulation results. Okay, so now if we look at the results, you see that clearly that there are three scenarios we actually have from different Green boundaries. So I want to mention that this dashed lines are the bulk diffusivity at low concentration. Okay, so you see that for the first row, so you see exactly the same diffusivity, bulk diffusivity, although you have Green boundary. Well, for the second one, you have much faster diffusion, so the diffusivity is order of magnitude larger. Well, for the third category, so the diffusivity is much lower. So you see the line I'm pointing to is actually the black line. The black line corresponds to 300 Kelvin. I've also include the data for other temperatures. But let's focus on 300 Kelvin just to have a systematic comparison. You see that we do have three scenarios: bulk-like, fast diffusion, and slow diffusion. Okay? So now we know that for different Green boundary, you do have different diffusivity, but apparently that depends on the Green boundary characteristic. So how do we actually try to have a structure property relationship? Okay, so for that, then we choose a particular representative of Green boundaries. And we choose 100 symmetric tilt Green boundaries. And because this Green boundary is relatively regular, so you can actually do good analysis of the Green boundary structure as you vary the tilt angle. Okay? And now if we plot the diffusivity for this set of Green boundary, you'll see that as the tilt angle varies for the left and right regions, you have the diffusivity much lower than the bulk diffusivity. Of course, it depends on the bulk concentration. And in the middle, then you have actually much higher diffusivity. Okay? So you see there's a systematic variation of the tilt angle, and you see two drastic different diffusion scenarios. And there's two slow diffusion, we can call it slow diffusion. Well, the middle is fast diffusion. And interesting, if you look at the tilt angle, these two regions are actually low angle, so it's not a typical kind of low angle Green boundary, because if we use a typical low angle, it would be much smaller than this. And you may wonder, if you're not really familiar with Green boundary, why this is low angle? It's because of symmetry. Okay, so because of symmetry, this region is also low angle Green boundary regime. While in the middle is high angle. So that makes us wonder, okay, so why is such a drastic transition from low angle to high angle? Then you get diffusivity suddenly jump from this value to here. Okay, so this makes us think, okay, so what happens? For low angle, we know that nicely we can actually use a dislocation model to describe it. And with the angle is small, so basically you can describe the Green boundary as kind of a series of dislocation, kind of a space along Green boundaries. And we know the dislocation serves as the trap site. So basically this would be kind of the energetics, the picture you expect. And the trap site meaning that energy state is lower. So it's effective trap hydrogen and give effective overall low barrier. Although at the core region, you can have a low barrier region. But basically this is what you expect. So this is a kind of individual barrier, high barrier region, and then followed by the bulk diffusion. And you can actually describe this use classical Frank-Billy relation. Okay. And in fact, this is what, if you actually look at the barriers, this is what you see from the Atomistic picture, from contour plot I showed before. Okay, and indeed, if you look at these two regions, you can actually reasonably well predict the diffusivity using a classical trap model, the Mechanistic force model. So you basically you can actually look at depends on the spacing. So as the angle increase, and you have more trap sites and more trapping densities, and the diffusivity decrease. So it's a classic picture as expected from this equation. But for the high angle regime, then you see that we have shown before that you have the fast diffusion channels. So that turns out to be because in the region, well, you have the core overlapping, or whatever you interpret that. And this core overlapping, atomistically speaking, so that's actually distort all those polyhedrons that constitute the ground boundary, and then gets all those paths connected. Okay? So this is basically the reasoning for that fast diffusion. And based on this picture, then we can actually predict when this transition will happen, because we basically have described this fast diffusion attributes to core overlapping. So we can actually precisely calculate when it occurs, and combining this Frank-Billy model with the polyhedron analysis, we can identify the core overlapping happens when basically the separation between two individual dislocation core is 2 times the Box factor. So basically, effective that if we take the Box factor to be the core radius. Okay, and if we combine these two together, you see that we nicely predict when the transition happens. Okay, with that, that basically concludes my talk. But if I may, I guess I still have a couple of minutes, right? I want to mention that this actually one thing is that one can easily get carried away by this result, because it's showing, oh, it's really like slow diffusion or fast diffusion. But we need to be a bit careful when we actually try to interpret this result and connect this to experimentally measured diffusivity, because what we are measuring is actually the overall diffusivity. So basically, we count all those hydrogen inside the system. The way we calculated it, we take basically the mean squared displacement for each individual hydrogen. But when you're measuring in experiments for the permeation test, then, well, I'm not an expert, but I know one way is that you take the transit region and you get the effective diffusivity. That's more or less is the integration of diffusivity from different concentration. And you can see that from this picture, the diffusivity is really concentration dependent. So this, you need to take some caution when you actually directly use the result to interpret fast diffusion or slow diffusion from experimental measurement. Okay, so with that, I would like to conclude the talk, and this is some summaries, so I won't read it. But basically, we have demonstrated there are 2 scenarios, fast diffusion and slow diffusion. Again, the fast and slow is relative sense. And then we have some dislocation model, make use of dislocation model to predict the angular dependence. Okay, and last, I acknowledge the support, and thank you for your attention, and I welcome any questions.
Okay, we have time for 1 or 2 short questions. I think you were first. Yeah, you're first.
Oh, okay.
And then after.
And you tried to explain the example of diffusivity from a low angle to a high angle.
Right.
With some part of connectivity.
Right.
So still we see the difference in the region of high angle boundary, and at 30 low and at 60 degrees, 2 order of magnitude high. So how did you explain the
that's a very good question. So this one, we don't have a predictive model for the diffusivity. So basically, what we did predict is a threshold. So I have, I think I have some backup slides. So if you, this essentially is actually atomistic. So basically because if you going from here, so even if we look at Frank-Billy, you see that these 2 regions are both low angle. Well, again, relative low angle. And you see that the constituting dislocation is different. So that actually tells you the polyhedron that's constituting ground boundary is also different. So when you change, so the core overlapping actually also is different. So the threshold at which the core overlapping happens, you see that the ground boundary structure, the core overlapping are not the same. So it's really fundamentally depends on the polyhedron that's constituted in ground boundaries, and depends on volume distortion. we have another so basically like if you look at the volume distortion of course this line is not supposed to be this. So basically like if you look at, so here, I don't know whether I have time to describe it, but basically if you look at the controlling polyhedron volume, then here at this region, like the distortion is much more significant. So there's more facilitation of hydrogen diffusion.
Distortion is larger.
Yes, it's larger. So but this is a very localized distortion of the single polyhedron. So this is just like one possible reason for the difference. Okay. Yeah, we can discuss further. Richard?
Very, very quick question.
Yeah, just wanted to know your comments because your calculations show that specific grain boundaries can work as traps. They show a higher affinity for. Do you expect also them to show a kind of degradation in mechanical properties?
We don't know. We don't know whether that will lead to degradation. That's too big a question for me to answer based on my current results. Yeah, but the trapping. Well, I guess like trapping. If you just look at individual dislocation, that's alone. I don't foresee that just that trapping alone would directly lead to degradation.
Sorry, we have to move on. No, sorry. Okay, thank the speaker one more time.